One, we're very happy to share our papers on multiple instance learning via iterative self-paced supervised contrastive learning. In this paper, we aim to tackle the multiple instance learning problems where we have a backup instance, but we don't have instance level labels. We only know the back level labels to tell us whether there is at least one positive instance per bag or not. This is a pretty challenging problem, as a bag can contain more than 1,000 instances in very typical applications such as pathology. Therefore, learning a very nice representation for each individual instance when only back level labels are variable is very important in this task. In this paper, we propose a framework that iteratively improves instance level features by jointly estimating latent instance level pseudolabels. To this end, we alternate between these two steps and get better performance. Traditionally, what people do is that they first pre-train a feature extractor and then train an aggregator that maps the features to back-level prediction. Since the bag size is actually very large normally, it's not possible to train from end to end. So this stage, feature extraction, is actually very important. The sort of method for that is use contrastive self-supervised learning, which means that you random sample some instance as negative pairs and you push them apart where you push the augmentation of the same instance closer. However, in this scenario, there is an issue. Since the prevalence of the positive instance can be very low in bags, so most of the instances are actually negative. When you sample the pairs that are supposed to be the negative pairs, they actually belongs to the same class. So to this end, the contrastive learning actually push apart representations of negative instance, just as in the red panels, when they should be pulled together. And that will result in a less discriminative representation. What we propose is that we leverage the pseudolabel learned in the multiple instance learning aggregator and use that to get a training of the feature extractor to do some fine-tuning. And since you have a better instance representation, you can get better pseudolabel, so which iteratively helps you to conduct another round of fine-tuning. So the idea is that we alternate between feature extraction and aggregator training. And with light, we have pseudolabel. So what we use is supervised contrast learning to get the fine-tuning instead of the unsupervised way. The things like the pseudolabel are not perfect, and we need to have some measures to tackle the imperfect pseudolabel that will follow us in the following section.
To solve this problem, we propose a self-paced sampling strategy, which can dynamically adjust the negative and positive pairs to mitigate the errors in the pseudolabels during training. The sampling strategy with self-paced learning is based on two assumptions. The first assumption is that better representation can lead to better pseudolabels, and vice versa. And the second assumption is that the instances in the negative bags are always negative. So we use these two assumptions to improve the quality of contrastive learning. Since negative bags only contains negative instances, we start with a few warm-up epochs where we only sample query images in the negative bags, which guarantees that they are all clean labels. After that, we sample instances with high confidences in their pseudolabels, which are the darker parts of these two plots. They usually have relatively high accuracies. We start with a small range of them to ensure high precisions at the beginning. Then we gradually enlarge the range to include more samples as the pseudolabel quality improves. These two methods can help us to improve the quality of contrastive learning during training. So this plot shows the AUCs of instance pseudolabels during training. It demonstrates that our model is able to iteratively improve the pseudolabel accuracy during training, and both iterative updating and self-paced sampling are critical to achieving better performances. In our experiment, we apply our framework on 3 multiple instance learning datasets in healthcare applications. We use 2 histopathology datasets chameleon 16, which is for tumor detection, and TCGA, which is for gene mutation detection. The histology images are usually too large to fit in the GPU memories, so they are cut into patches, but they usually only have slide level labels. We also use the ultrasound dataset for breast cancer detection, where several pictures are taken when scanning different parts of the body, but only one diagnosis is provided for each patient. On all of these three datasets, our framework consistently improved the traditional multiple instance learning baselines, where we only pre-train the instance representations with self-supervised learning methods like Sinclair. Besides the back-level performance, we also evaluate the instance-level performance on chameleon 16 dataset, where we have the access to the ground truth instance labels. The table shows that our framework improved the instance-level prediction accuracy regarding various metrics. And the visualization in the lower plot demonstrates a better capability of our framework to localize those tumor cells. This result shows that our framework can improve both back-level and instance-level predictions in multiple instance learning. We also evaluate the compatibility of our model with different multiple instance learning aggregators. The table shows that the representation learned by our framework can consistently perform better than SSL pre-trained representations when applying different aggregators in the downstream tasks. Besides comparing different aggregators, we also evaluate how well our framework can generalize on different pre-trained weights. We experiment with different pre-trained instance representations, including ImageNet pre-trained weights and several commonly used SSL methods. The table shows that our framework can consistently improve the performance based on the initial representations trained by different models. Both experiments show that our framework can be easily adopted to different multiple instance learning models. Although we previously mentioned that in most cases, end-to-end training are not feasible in multiple instance learning due to very large batch sizes, we still compare our framework to end-to-end training on both the feature extractor and the aggregator simultaneously. We found our framework can still perform better when the end-to-end training are feasible on some datasets. This further supports the effectiveness of our framework on various multiple instance learning problems. Thanks for watching our presentations. So if you are interested in our research, please join us during the poster sessions. Thank you.